Hey there. Let's look at this one, and what we've got here is a car. It's going in this circular path, and it tells us that r, that radius there, that radial line, is 400 cosine theta, and here's theta right here. Now it also says that the car travels around the circular track, such as its transverse component is theta equals 0.0062 t, or t squared, sorry, radians, where t is in seconds. And it wants us to find the car's radial and transverse components of velocity and acceleration when t is 4 seconds. Now, first of all, I know this is a polar coordinates problem just because of what it's asking for, right? It wants radial and transverse components. But even if it didn't ask for that, I would still use polar coordinates for this, just because I've got this radial line measured to our car or particle that's moving along a circular path, and then I've got this angle theta that changes as the car moves. Okay, so either way I would know to use polar coordinates here. Now we want the radial and transverse components of velocity and acceleration. So first thing I want to do, let's write down our equations for velocity and acceleration in those coordinates. For velocity, we're going to have r dot u sub r plus r theta dot u sub theta. And then for acceleration, we have r double dot minus r theta dot squared u sub r plus r theta double dot plus 2 r dot theta dot u sub theta. Okay, so in order to find these components, I have to find all of these terms, right? I got to find all the r terms and all the theta terms. So let's go ahead and do that. And remember, we want t to be 4 seconds. So let's start with theta. They gave us this equation here. So let's write that out. All right, so 0.006 t squared. Now I want to find theta dot because I need it here, and here, and here. So theta dot, all that is the first derivative of theta with respect to time. All right, that's all that is. Okay, so we look up here, take the derivative with respect to time. So we're going to have 2 times 0.006 t. And that is 0.012 t. Not too bad, right? Now we need theta double dot for right here. So that's just going to be the second derivative of theta with respect to time. So let's look here, take the derivative. Well, we get 0.012. Right, not too bad so far, right? Now, we want these values when t is equal to 4 seconds. So let's find that. All right, so theta then will be 0.0064 squared. All right, so just plug in 4 for t. Theta dot will be 0.012 times 4, and I'll put the numbers out here in just a second. And then theta double dot, that's constant, so that's just 0.012. All right. Now our theta, once you plug this into a calculator, is going to be 0.096, and that's going to be radians. All right, we know that from right here. And then theta dot, just multiply these together, will be 0.048. That'll be radians per second, and units here will be radians per second squared. All right. And keep in mind when you're using these equations, you should have radians here. Okay, you don't want to use degrees. Now we got our thetas. Let's look at r. So r is usually the tricky part because typically the derivatives are a little bit harder on this one. So r is just 400 cosine theta. Okay, so we've got that. Now let's do the derivatives and we'll plug everything in. Let's find r dot. All right, so that's the first derivative of r with respect to time. Now I know you might be looking at this and you're thinking, but wait, there's no time in here. That's true, but theta changes with time, right? So we can't just ignore that because our theta is not constant. It's changing as the car drives along the path. So that means we have to take the derivative there. So let's go ahead and see what we get. So basically you're going to use the chain rule. All right, so derivative of 400, that goes to 0, so we don't have to worry about that. Then when we get to the cosine, we're going to have negative sine theta, right? So we got negative 400 sine theta, and then we have to take the derivative of theta. So we'll have theta dot. So let's rewrite it in a better order. So we have negative 400 theta dot sine theta. Okay. Now let's find our double dot. So this will be a second derivative with respect to time. We're going to use this. All right, chain rule again. Negative 400, that doesn't have a derivative, goes to 0, so we can forget about that one. Theta dot does have a derivative because it's changing with time, right? So we're going to have negative 400 theta double dot sine theta. And then now we got to worry about the derivative here of sine. So we're going to have negative 400 theta dot from right here. Derivative of sine theta will be cosine theta. And then derivative of theta is theta dot. So let's simplify this here. All right, so this last term will be minus 400 theta dot squared cosine theta. Now we want these values at t equals 4 seconds. So let's go ahead and find out what that is. All right, let's do r first. So we have 400 cosine theta. Well, what was theta at 4 seconds? It's right up here, 0.096. Now notice this is in radians though, so you need to switch your calculator to radian mode here. Otherwise you'll get the wrong thing. Okay, so that'll be 398.16 meters. R dot, we're going to have negative 400. Theta dot, 0.048. And then sine of theta, which was 0.096. That gives us negative 1.84. That's meters per second. Finally, r double dot, our acceleration term here. So here's the equation. So negative 400 theta double dot was 0.012 sine of theta, so 0.096. And I'm going to write the rest down here. Minus 400 and then theta dot squared, so 0.048 squared cosine 0.096. And that is negative 1.377 meters per second squared. So not too bad if you remember how to do all these derivatives. Really, that's the hardest part on these problems, is doing the derivatives. That's always the part that gets everybody. So now let's go ahead and let's go back to these equations. We have everything we need to find the vectors. Okay, and let's write them back down here. So r dot is negative 1.84 times u sub r. And then we have r theta dot. R was 398.16. Theta dot was 0.048. U sub theta. So simplify this. First term there stays the same, negative 1.84. And then we've got 19.11 u sub theta. And that's meters per second. Now, it wants the radial and transverse components. Well, this is the radial component. This is the transverse component, right? So v sub r will just be negative 1.84 meters per second. V theta will be 19.11 meters per second. Just like that. All right, then we do the same thing for acceleration, except for we have this more lengthy equation here. So let's write it back down. So this first term will be the radial component, And then the second term is the transverse component. So let's plug in our values. R double dot, negative 1.377. And then minus R, so 398.16, times theta dot squared, so 0.048 squared. And that whole thing is the radial component. And then let's do the transverse. We need R again, 398.16, theta double dot, 0.012, plus 2 times R dot, negative 1.84, and then theta dot is 0.048. And then that's u sub theta. All right, so plug those into the calculator, and what you get is negative 2.29 u sub r. And then for the transverse component, you get 4.601 u sub theta. So that means a sub r is this term, so negative 2.29. It's going to be meters per second squared, and then a theta will be 4.601 meters per second squared. All right, that's how you go about getting your radial and transverse components. So it's not too bad once you figure out the derivatives, right? You get the derivatives, plug in your time, and then there you have it. All right. And one more thing I always like to do is let's kind of draw this on a coordinate system. It doesn't ask us to do that, but let's do it anyways. All right, so here's that curved path. Now let's say the car is right here. I'll just make it a dot. Okay, and I've got that horizontal axis right here, and then I've got this radial line going there. Okay, so let's define our coordinate system. So for the radial line, all we need to do is extend this out. All right, so that'll be a radial line. And I am assuming the car is going in this direction here. So the theta axis, or that transverse axis, will be right there. All right, because I was drawn in the direction of increasing theta. Now, there's a 90-degree angle there between those two. And now let's draw these vectors on here, these components. Okay, so let's start with a velocity first. So I've got a negative radial component, a positive theta component, right? So that means I'm going to be basically right here, all right, because it's tangent to the path there. So we got that, and then let's look at our components. I got a negative 1.84. So this would be negative 1.84. That's my v sub r. Notice it's in the negative direction because this was positive. And then we have a positive 19.11 in the theta direction. So that would be right here. So we've got that. Okay, and let's put this little angle alpha here. We'll find that angle in just a second. Now we got that for velocity. Let's look at acceleration. Acceleration, I have a negative r component, positive theta component. So that's also going to be over in this quadrant here. So let's just put it here. So it's, we got room. And that means we're going to have an a sub r, right, which is negative 2.29, and then we have that positive a theta here, so 4.601. Okay, and then we can find this angle. Let's call this one beta. Okay. All right, let's do alpha first. So alpha, notice we can use arctangent. So we'll have the arctangent, and then we'll have the opposite side, which is 1.84 over the adjacent, and that's 19.11 because this deals with the velocity here. And notice I didn't include the negative because I already know what quadrant we're in, so it doesn't matter. Now this one's going to be 5.5 degrees. You got to switch back to degree mode in your calculator. All right, and then finally this little beta, that's between acceleration and that theta axis. So that one we could do arc tangent, and we'll have 4.601 for here, and put that over 2.29. All right. Actually, you guys, I think I have this. This is backwards. Let's flip these around. Because tangent is opposite over adjacent, right? So opposite of this angle would be the 2.29. So let's flip that. And then let's see what we get. So we're going to get our tangent, 2.29 divided by 4.601. So 26.46. Okay, so there you have it. So that's kind of how you could draw it out, look at your components on a reference frame using the R and theta axes. Okay, hopefully you like that one. Y'all have a good afternoon.